An electronic circuit, on the other hand, usually incorporates some device that enables the circuit to amplify. That is to say, a very small change in one variable over here creates a very large change in a variable over there. And one of the typical things that we add to an electric circuit in order to make it into an electronic circuit is a transistor. I maintain that the surface of the sun exhibits the properties of a transistor. Is it a transistor? No, of course not. But this presentation of mine that I'd like to show you this morning came to me when I saw an analogy, at least I think I saw an analogy, between two things. And I firmly believe that important discoveries, breakthroughs in science are made by somebody who can look at an area over here and an area over there and recognize similarities between those two disparate areas of science. And if you can recognize a similarity between a problem that's been solved over here and one that hasn't been solved over there, maybe you can use those techniques over here and get some progress. I know that, for example, Hannes Alfvén did that. He was a Swedish engineer, and they were having all sorts of problems on the high voltage DC transmission lines in Sweden. And this is an example of one of those disasters. One pole of the switch over here, one pole of the switch over there. The switch is wide open, but the current says, I ain't stopping. And so you got this arc, and it's a sort of self-sustaining arc. Eventually it'll blow itself out, and when it does, it will probably create an explosion which in many instances killed people, blew up buildings, and was a major disaster. Alfvén was able to find out what the cause was. The cause was energy stored in the magnetic field around the transmission line, and when the circuit refused to open, that inductive, sort of like a water hammer in a hydraulic system, there was an explosion and the disaster occurred. Alfvén said, well, that kind of arcing there is sort of similar to the prominence arcing that we see on the sun. And when that prominence expands like that arc and breaks, we have an emission of stuff which is called a CME, a coronal mass ejection. As long as it's up there by the sun, we don't worry about it too much. If it happens in Sweden near a village, we do. So, but nevertheless, the response, the cause of this was, Alfvén felt, the same cause, magnetic field energy, that caused the problems with the transmission line. Well, I'm trying to convince you that an analogy exists between our sun, which is our local star, which we all know pretty much looks like this. If you look at it through a backyard telescope, you see that's the photosphere. Occasionally you see some sunspots. If you've got a good enough telescope, you can see some structure around usually around the limbs, but you can't see anything else. And so you would conclude, well, that's the surface of the sun. Well, it's not the surface of the sun, because there are other things above that layer. And this is what we typically see, the photosphere. It gives us all the light and the electromagnetic radiation that we receive. But it's not the top surface. The sun's surface really has three main layers. And there they are. This is a sketch. You can see the curved surface of the sun is the yellow. The Earth is in here to scale, by the way. It shows how small the Earth is in comparison to the sun. There's the photosphere. That's that layer that surface that we see. And by the way, and I'm not going to continually bug you with this, but at every step along the line of my talk here, there should be a question in the back of your mind: how does the standard model explain that? And I'm not going to continually poke at them, but I think you should keep that in mind. The standard model, I'll say it once and then I won't do it again, has no explanation for why the chromosphere exists. The chromosphere is this set of spicules or spikes that stick up. We can see them during a total eclipse of the sun. And of course, above that is the vast corona that we all know about. This photosphere has sunspots, the chromosphere has spicules, and the corona has the shapes as caps and striations and filaments. If we look at the photosphere close up through a really good telescope, we see that it has a granularity to it. The astronomers call those granules. Well, my hero, Ralph Jurgens, took a look at that, and he said, that to me looks like a plasma cells. And so he then investigated what a real plasma discharge looks like in the laboratory and what the structure of it was. He concluded that these cells were really what we'll talk about as anode tufts. It's a tufting that's seen in the laboratory if you have a good enough microscope and you can look at the anode very closely. If you look closely at this picture, you'll see that between the anode tufts, between the granules, there are black channels that permeate and run and separate the tufts. And within those channels, can you see the tiny little white dots? I don't know if you can see it or not. Those are the spicules. So the question arises, well, why is that stuff there? What do the spicules do? How do they contribute to the action? The tufts come and go over periods of like minutes, hours, perhaps a day, but no more than that. These tufts, they are plasma, and they are in the arc mode. You know, there's 3 modes of plasma: arc, glow, and dark current. This is the powerful arc mode, and that's why all of the heat and light get irradiated from this area. The temperature, though, is about 6,000 Kelvin, which it's pretty hot. I wouldn't want to be there, but it's as far as the temperatures of plasma is concerned, and certainly temperatures of the sun's corona are concerned, it's very cool. There's the plasma discharge that Jurgens looked at. In the days, in the beginning of the 20th century, even back in the 19th century, people were very concerned about the cathode and what was the structure of the charge layers and voltages and forces at the cathode. They paid relatively little attention to the anode. The tufts are represented by this anode glow, which we see. And notice that the thing is, this structure, this plasma cell, the anode glow, is separated by a small distance from the anode itself. In the electric star, the electric sky, the electric sun model, the anode itself is the body of the sun. Here are the tufts, and then right connected to and emanating at a further distance from the sun itself is this positive column. The positive column is another cell of plasma. It's in the glow mode and has certain properties that we'll discuss. But the typical sunspot, there is a typical sunspot. You can see the tufts around here. In the penumbra of the sunspot, the tufts look elongated, and in the middle of the umbra, the dark part of the sunspot, there are no tufts. So bear that in mind. A sunspot is a place where there are no tufts. There is no tufting. Well, so what? Well, we'll see. The chromosphere is that bunch of spicules. Here's an example. It looks like a prominence beginning here. That's about 2,000, 3,000, 5,000 kilometers high. The sun, of course, is like 800,000 kilometers across. So it's a relatively thin zone, the chromosphere. It's generally H alpha. H alpha is a spectral line right in the middle of the visual. It's in the red, the deep red color. There's the spicules about that high. It's usually filamentary. You can see the streaks. It's not just a uniform glow. It has fingers. And there's a reason for that, and it's a well-known plasma property of glow mode plasma that they usually filament. Seen only during eclipses. Again, I asked the question, why is it there? It changes shape depending on whether it's a time of active sun or quiet sun. This is what it looks like during the quiet sun. This is what it looks like during the active sun. The active sun is a time when there are a lot of sunspots. The quiet sun there are much fewer sunspots. You can see here, one thing that, not really germane to what I'm saying, but you can see the magnetic fields that are also filamented. You're not looking at the magnetic fields, by the way. Astronomers say that all the time, and that's not true. Magnetic fields are invisible. What you see, like here, is plasma, which is surrounding currents that follow the magnetic field. So it's the magnetic field's there, a current follows the magnetic field and lights up the plasma so we can see it. Here's one of the biggest problems facing modernist solar astronomy, and that's this sun temperature profile. This, if the sun is just a furnace that burns hydrogen and turns it into helium, much like a wood furnace turns wood into carbon and oxygen, as you get farther away from that furnace, you should get less radiation. The temperature should go down. And as you begin to go away, right here, that's exactly what does happen. But all of a sudden, there's an anomaly. And the farther you get away from this stove, the hotter it gets. Temperature goes up. Until finally, when you get out here at the top of the spicules, the temperature shoots up to like 1,000,000 Kelvin. Now that is hot. How? How can you get a high temperature like that out here when the temperature of the photosphere is only about 6,000 or 7,000 Kelvin? Good question, and I will endeavor to say why. An electronic circuit, on the other hand, usually incorporates some device that enables the circuit to amplify. That is to say, a very small change in one variable over here creates a very large change in a variable over there. And one of the typical things that we add to an electric circuit in order to make it into an electronic circuit is a transistor. I maintain that the surface of the sun exhibits the properties of a transistor. Is it a transistor? No, of course not. But this presentation, breakthroughs in science are made by somebody who can look at an area over here and an area over there and recognize similarities between those two disparate areas of science. An innovation of mine that I'd like to show you this morning came to me when I saw an analogy, at least I think I saw an analogy, between two things. And I firmly believe that important discovery